So what does this fusion discovery mean for
Many
us?
people, when they think of nuclear energy, they think of nuclear fission, which was the energy source in the two bombs used in the Second World War. Very quickly after that, we magnified the energy of those bombs by creating a whole other kind of bomb, which came to be known as hydrogen bombs. The hydrogen bombs don't have the radioactive baggage that fission bombs do. Hydrogen bombs are fusion. So fission, let's back up. Fission, you take a big atom, break it, and you weigh those two atoms, and they weigh less than what you started with. Where did the mass go? E equals mc squared. The mass went to energy. You can do the same thing, but coming from the other direction. You take a very light atom, hydrogen, fuse it together with another hydrogen atom, and you get helium. And your product has less mass than you started with. Once again, you get energy, but you don't have all of the byproducts. We've made fusion for 60 years. The problem was we don't have controlled fusion. And when we don't have controlled fusion, it's called a bomb. But when you control it, then you can throttle it, you can valve it, you can put it where you need to and how you want to use it. And so right at this moment, I don't think people know for sure what the announcement will be. But if the Secretary of Energy is giving the press conference, everyone I think is thinking that we finally can get out more energy than we put in, and that is the...
Oh, and that has been the key, because for so long we've been trying for decades.
It's been the holy grail, and I thought we would have reached that in the 80s,
yes,
but then we didn't. Maybe it's because peace broke out in Europe and people took less interest in what physicists could do.
Yes, and we had a different type of nuclear energy for quite some time.
Well, that's right, that's right. No, but there was physics labs still working on this. Here's the problem. In order to have fusion, you need very hot plasma, which is like an ionized gas. So hot that it can't touch anything that might contain it. If I give you plasma and put it in a suitcase, the suitcase would vaporize. So one of the great problems is the containment of such very high temperature gas. And because the gas is like ionized, which means there are free electrons moving around, you can contain it in a magnetic vessel, a magnetic bottle, a magnetic shape, so that it tries to escape it, but it can't, because it's charged and it repels the magnetic field. These are the challenges that the physicists faced for decades.
All right, so let's say we've overcome some of those challenges and finally created more energy than we put into the experiment.
That's it.
So when do we get fusion stations? When do I get to plug my car in the fusionorium?
So now it's up to the engineers.
Okay.
Once we get the physics figured out, which it seems like we have, then the engineers say, can I make that smaller? Can I make it portable? Would it fit in a car? Or is it only the size that might power a city? There are places that don't have access to energy, either oil or even sunlight, for example, and so, or tidal or hydro. So this would be transformative to civilization. And I see it akin to the transition from horses to automobiles.
Yes.
Which happened in a matter of a couple of years because we got the physics figured out for engines and internal combustion engines. And when that happened, you couldn't give away a horse, yet we were riding horses for thousands of years, building civilization literally and figuratively on its back. So my analogy to that is, we've been digging fossil fuels out of the ground for 150 years.
How long will it take to heal the planet from any harm that we have done to ourselves?
Yeah, because here we are, like
carbon emissions,
harming a planet that itself was trying to sustain us.
Yeah.
That's not by doing that, you've sown the seeds of your own extinction.
Welcome, everyone. It's so great to see members of Congress here. Senator Reid, so glad you're here. Congressman Swalwell.
Ask the Ukrainians to help them cheat an election.
Today, we're here to talk about fusion, combining two particles into one. Last week, at the Laurence Livermore National Laboratory in California, scientists at the National Ignition Facility achieved fusion ignition. And that is creating more energy from fusion reactions than the energy used to start the process. It's the first time it has ever been done in a laboratory, anywhere in the world. Simply put, this is one of the most impressive scientific feats of the 21st century. This is a BFD. Researchers at Livermore and around the world have been working on this moment for more than 60 years. So, what does this accomplishment do? Two things. First, it strengthens our national security because it opens a new realm for maintaining a safe, secure, and effective nuclear deterrent in an age where we do not have nuclear testing. Ignition allows us to replicate, for the first time, certain conditions that are found only in the stars and the sun. And the second thing it does, of course, is that this milestone moves us one significant step closer to the possibility of zero carbon, abundant fusion energy powering our society.
Thank you, Administrator Ruby. A paraphrasal of Abraham Lincoln strikes me as fitting here. The world will little note nor long remember what we say here, but it can never forget what they did at the National Ignition Facility. So let's recap. A team at Laurence Livermore National Lab, National Ignition Facility made the following happen. There's a tiny cylinder here at the end of this that you probably can't see. It's about so tall and this wide. Inside that was a small spherical capsule about half the diameter of a BB. 192 laser beams entered from the two ends of the cylinder and struck the inner wall. They didn't strike the capsule, they struck the inner wall of this cylinder and deposited energy, and that happened in less time than it takes light to move 10 feet. So it's kind of fast. X-rays from the wall impinged on the spherical capsule. Fusion fuel in the capsule got squeezed. Fusion reactions started. This had all happened before, 100 times before. But last week, for the first time, they designed this experiment so that the fusion fuel stayed hot enough, dense enough, and round enough for long enough that it ignited, and it produced more energies than the lasers had deposited. About 2 megajoules in, about 3 megajoules out, a gain of 1.5. The energy production took less time than it takes light to travel 1 inch. Kind of fast. So this is pretty cool.
This is a historic achievement for the team at Livermore, our collaborators in academia and labs in the US and abroad, our industry partners, the fusion community writ large, and the many supporters and stakeholders in the National Nuclear Security Administration, the Department of Energy, and in Congress, who've ensured we could reach this moment, even when the going was tough. Over the past 60 years, thousands of people have contributed to this endeavor, and it took real vision to get us here. Building the National Ignition Facility was an enormous scientific and engineering challenge. I like Dr. Prabhakar's emphasis on the importance of bringing those two together. In the end, after all that work, the laser has exceeded its performance goals, opened whole new areas of high energy density science to exploration, and delivered the data we need to keep our nuclear deterrent safe, secure, and effective. Our pursuit of fusion ignition over the past decade at NIF was an incredibly ambitious technical goal. Many said it was not possible. The laser wasn't energetic enough. The targets would never be precise enough. Our modeling and simulation tools were just not up to the task of this complex physics. Progress has taken time, but last August, when we achieved a then record yield of 1.35 megajoules, putting us at the threshold of ignition, many took notice. And last week, our pre-shot predictions, improved by machine learning and the wealth of data we've collected, indicated that we had a better than 50% chance of exceeding target gain of 1. 60 years ago, when John Knuckles and his team proposed that lasers could be used to produce fusion ignition in the laboratory, it was beyond audacious. The laser had just been invented and was far from the mature tool we know today. But this is really what national labs are for: tackling the most difficult scientific challenges head-on, learning from the inevitable setbacks, and building toward the next idea. Laurence Livermore has been at the center of the ICF community across these many decades, and ICF has been a centerpiece of our lab. Indeed, people often say that LLNL stands for lasers, lasers, nothing but lasers. But I think our motto sums up our approach nicely: science and technology on a mission. This achievement opens up new scientific realms for us to explore and advances our capabilities for our national security missions. It demonstrates the power of U.S. leadership in science and technology and shows what we're capable of as a nation. And as the Secretary mentioned, breakthroughs like this one have generated tremendous excitement in the fusion community and a great deal of private sector investment in fusion energy. But this is only possible due to the long-term commitment of public investment in fusion science. The science and technology challenges on the path to fusion energy are daunting, but making the seemingly impossible possible is when we're at our very best. Ignition is a first step, a truly monumental one that sets the stage for a transformational decade in high energy density science and fusion research, and I cannot wait to see where it takes us. Thank you.
So I'll ask you a question. Do you know that the sun is a continuous fusion reaction?
Naturally.
It has a continuous. You big dumb bitch. Large atoms apart. Gave off tremendous amount of energy. But there's another amazing thing that happens in nature where you smash tiny, tiny parts of atoms together, protons, and they fuse and convert a tiny amount of their mass into energy, into heat and light. And that was the mythic hydrogen bomb. But for all this time, for 80 years, people have tried to get this idea where you could do it in a controlled fashion using a tiny amount of material. And the material would be hydrogen that has an extra neutron, which has this marvelous word deuterium. And then if it has 2 extra neutrons, that's tritium. And so using lasers, they zap this container, this whole rum, this gold thing with the deuterium in it, and the lasers create X-rays, and the X-rays create constructively interfering shock waves that get the thing to fuse without a giant magnetic bottle and without the gravity of a star. And so this is the first time, by all accounts, they've gotten more heat out than they put in. And this is amazing. And there's, as far as I know in the reporting the last few days, no one's mentioned that Enrique Fermi and his colleagues in the University of Chicago did the first chain reaction, which led to all the nuclear power plants we have now, on December 2nd, 1942.
Okay.
So it's quite a little chin stroke that it's very close to 80 years later to the day that this breakthrough occurred. And so you guys, if this would work, if this is a harbinger, if this is really the beginning of something huge, it would change the world.
Thank you for explaining that to Allison.
Well, no. I was going to say all of that, but Bill Weir, tell us what we need to know.
Bill just did.
In addition to
anyone over with dates at the band? No, it's a star in a box. This is the whole idea. This is why nuclear physicists have been salivating on this idea forever. It's taking a star and putting it in a box on Earth and tapping that energy that goes forever. It's what Iron Man has in his chest, okay?
Now we understand.
It's this endless clean energy machine, and the appeal of it is you don't have any nuclear waste, there's no fallouts, there's no accidents. We don't have to drill or mine for fuel anymore because the fuel is seawater. We have 30 million years of seawater, theoretically, to feed these machines. But what Bill was describing there, these 200 lasers aimed at what is essentially a peppercorn of hydrogen,